All right, hey Chase, this is 3-4 related rates. Talking about sand in an hourglass, yeah? Okay, it's the same way with water in an hourglass, but let's pretend that this is an hourglass right here. You don't have to draw this if you don't want to. But there's the bottom of my hourglass, right? The water, or the sand is pouring into the bottom, okay? Now, when you first tip it over and it is like plumb full, it doesn't really look like it's, like you can't even see it moving down, right? You might be able to a little bit, but you can't really see it changing a whole lot. But then the closer it gets to the bottom,
the faster it moves.
the faster it looks like it's going down, right? But it's still coming out of the little hole at the bottom at the same rate, right? Like this is dripping out of here like however many grains per second or whatever it is. But it looks like it starts to go faster at the end, okay? So we're talking about like the rate at which things are happening. So let's talk about three different things. Let's talk about the rate of change of the height. Let's talk about the rate, I'm just going to call it ROC. ROC of the radius. And let's go rate of change of the volume. Okay?
The height, the radius.
The rate of change of the volume. Okay. All right, one of those three things is staying the same.
The volume. No.
All the way through.
Yeah, the volume.
The volume, right? The grains are leaking out, or whatever sand, water, or whatever we're talking about, it is leaking out of the bottom at the same rate. The rate at which the volume is changing stays the same. True?
Would it be 0?
This is going to be constant. It's going to be whatever like the rate is. Like maybe it's doing, I don't know, 20 grains of sand per second.
Well, like,
I don't know.
So like
however many coming down.
Like this guy, he's stationary. His speed, his velocity, his whatever is 0 because he's not moving because he's staying constant.
But these are moving, so it would be like some number.
Okay.
It would be a number, but it would be a number
0
other than 0. Yeah. So like the rate of change might be.
Did Chase come in?
No, he has not. But they say that he's here.
Okay. Thanks.
Okay. So maybe the rate of change of the volume is 20 grains of sand per second, right? Theoretically, that is staying the same, okay? The rate at which the height is changing, though, is not staying the same. In other words, this height is decreasing, but it's doing this. Are you ready? It's like going, and then all of a sudden it goes really fast. Did you see that? I'm going to do that again, okay? It's changing, and all of a sudden it's going really fast. You see that? Okay, that's what the height is doing. So the height, the change of the height of the, whatever the water is or the level of sand, that would be like this height right here, it is speeding up as it gets closer toward the center, okay? So the rate of the change of the height is going to be different depending on where the water level is at or where the sand level is at. So it will be speeding up. Does that make sense? What about the rate at which the radius changes? Okay, the radius is like around here, okay? Like this little oval right here, or like the radius there. If we talk about this oval, it's gonna look like as he goes down that he's only changing ever so slightly until we get to the very, very bottom, and then it goes really fast, right? So the rate of the radius changing, or the circumference of the circle, like at the very top of the water level, is going to look like it's going to speed up as well as it gets smaller, right? So it's going to speed up as well. Does that make sense? Do you see what I'm saying when I'm saying rate of change, like of the height, how the height is increasing, decreasing in this case? It looks like it's speeding up as it gets closer to the funnel, right? Or to the tip of the funnel, okay? So that's what we're looking at happening. Now, we've talked about the word rate of change before. What does rate of change represent?
The slope.
Derivative. Okay, or slope of the tangent line, but rate of change is represented by a derivative. So we're going to be doing derivatives when we talk about rates of change, okay? The rate at which the whatever is changing, the height is changing, the radius is changing, all of that stuff, okay? They are using a cone for these first three problems here. And so what we're going to do is we're going to look at this. This is the volume of a cone. We have water inside of a cone. Volume is pi over 3, or actually,
What?
1/3 pi radius squared h. Okay, that's the volume of a cone, but do you see what they did? They just lumped the pi onto the top. So if this formula looks a little foreign to you, 1/3 pi radius squared height, that is what we have going on here, okay? Now, when we're taking the derivative, we're not doing d whatever dx anymore, right? We're not doing that anymore. We are doing d whatever dt now, because we want to relate everything back to time. Like a rate of change is something per second, or something per minute, or something per hour, right? My bottom number is going to be time. So we're doing everything in relationship to time now. Time is my designated variable, okay? So let's do this really quick. They've done this below, but I'm going to do it off to the side over here so that we can see how this works. We are going to find the derivative of this thing. Volume equals 1/3 pi radius squared h, okay? All right, so here's what we're going to do. We're going to find the derivative of v. What's the derivative of volume? Yeah, it's like 1 dv dt, right? Kind of like the derivative of y is dy dx, right? The derivative of v is dv dt. So every variable that we take the derivative of, we're going to have d whatever dt. d whatever dt. Okay, now, how do we find the derivative of this? What do we have to use? The product rule. Okay, so I have an r and I have an h. Those are my two variables. Let's do this. With the r, let's call that whole thing my f, and let's call h is going to be my g.
You can do that.
You can totally do that, because these are just numbers. 1/3 pi is just a number in front, right? So this would be like the same as just like 3x squared. I can take the derivative of him, because those numbers in the front are just numbers, not variables, okay? So we need to do, I'm going to do equals f prime g plus g prime f, okay?
Is that down below?
Yep. They've done this down below. Like the answer to this is down below. But it makes more sense if we just like do it together. That way you know where it comes from, okay? So if I'm taking the derivative of f, the only thing I'm focused on is the r squared. The 2 is going to come down in front, right? So the 2 comes down in front. 2 times 1/3 is 2/3. Can we write it as 2/3 pi? He would be r to the first power. I didn't leave myself enough room.
Okay, neither did I.
R to the first power, but then on the end I need
Do you have to have h?
dr dt. Because we took the derivative with respect to time, we need dr dt, okay? So do you see where I get that derivative from? The 2 comes down in front, 2 times 1/3 is 2/3. The pi stays because it's just a number, r to the first power, and then dr dt is the
Do you have
derivative
to
of
have
r.
the 1?
No. You don't have to have the 1. I was just showing you. Yeah.
Is the r,
So-
why is it dr over dt?
Because I took the derivative of r with respect to time. Everything is d whatever dt. Like volume was dv dt. Right?
Because we're
Okay.
solving for r.
Because we're taking everything with respect to time. Okay.
What's the temperature in your room?
I don't know. Is it hot?
I'm hot.
You have a sweater on.
You were also eating soup.
True. Fan yourself. Okay, what is g? What's the g part?
H.
H, okay? Then we need g prime. What's the derivative of h? What's the derivative of h? 1 dh dt, right? 1 dh dt. Or you can get rid of the 1. We don't need the 1. And then f, what?
Are we going to get rid of all the dt's?
They're going to tell us what they are. We're going to plug stuff in for those.
That just sounds icky.
Yep, it's not too bad. It's not too bad. And then 1/3 pi r squared is f, okay? So to clean this up, I don't know if we want to clean this thing up. dv dt is going to be off to the side over here. I am going to put this all junked together. So I have 2/3 pi rh dr dt. I'm just going to plug the h in there. Plus
1/3 pi
1/3 pi r squared dh dt. Can I do that? Okay, so I have like these two pieces basically on this side, okay? And they will say, find the rate of change of the volume when r equals 2 centimeters, the height, I'm going to say h equals 6 centimeters, and the rate of change of r equals 1 centimeter per second and ROC of the height equals 2 centimeters per second.
Why?
Well, that's a lot of information. They will give you all of these things, okay?
ROC of the
Find the rate of change of the volume when the radius is 2 and the height is 6, and the radius is changing at 1 centimeters per second, and the radius or the height is changing at 2 centimeters per second. This is what they will give to you. So we're finding this stuff. Okay? They give you all the other information. When it says when R equals 2, that means we're plugging 2 in for R. When H equals 6, that means we're plugging 6 in for H. Right? What is the rate of change of R? What piece up here stands for the rate of change of the radius? What?
DR.
dr dt, the rate of change of the radius. This is another way of, a fancy way of saying that, hey, dr dt is equal to 1, right? Then what's the rate of change of the height?
DR or DH.
That's dh dt. So they're saying dr dt is this, dh dt is this. What are they asking us to find? The rate of change of the volume, which is, we are trying to find dv dt, right? So dv dt equals, this is what we don't know, okay? We have 2/3 times pi. What is R? 2.
I'm working
H
down my
is
piece
6.
again.
You don't have to write this down if you don't want to. dr dt is, what was it? 1 plus 1/3 pi. R was 2. And dh dt was 2 also. And then we solve that and we get that, whatever. Do we want to continue to solve? You feel like we've gone this far? Let's just do it. Okay.
Are the afternoon classes regular times now? On Wednesday?
This is 12. 12 times 2 is 24. This is 8 pi plus 2 squared plus 8/3 pi. Yeah. Which is 2 and 2/3. So 10 and 2/3 times pi, whatever that is. What? What is it? 32 pi over 3, yes, correct. 32 divided by 3 equals times pi. Yeah, 33.5. Okay, so if those were the numbers, and I made those numbers up, the volume is decreasing or increasing, depending on what we're talking about, at a rate of 33.5, we're in centimeters,
So
cubic
that's
centimeters per second.
DV
dV dt. Okay, now volume is in cubic centimeters and the time is seconds. So dV dt, volume is in rates of cubic centimeters, T is in time in units of seconds. So 33.5 cubic centimeters per second. That is the rate that my volume is changing, right? Got it? Yeah, that's how that works, okay? Woo, that was a lot of stuff. All right, let's go down to example 1. I don't really care for example 1 a whole lot, but it's a very easy example to start you off with. I don't care for examples like this because it has no like context to it. I would rather talk about like a cone that you can visually see, like, oh, the volume is changing at a certain rate. This has no context to it, so we're just going to be plugging stuff in, okay? All right, so let's go to example 1. It says, suppose that x and y are differentiable functions of t. Differentiable functions of t. The equation of y equals x to the 3rd power, okay? So when I do these problems, I a lot of times like to do what my equation is, what I know, and what I'm trying to find. Every single time I do a related rates problem, I fill all 3 of those things in. The equation that I have, what I know, what I'm trying to find. And I guess maybe right next to equation you could put like the derivative, because I know at some point I'm going to have to take the derivative, okay? So, the equation that we have, y equals x to the 3rd power, okay? I am trying to find dy dt. You see that?
What's DT?
DT. So this right here represents the rate. This is the rate that Y changes with respect to time. So is the Y coordinate changing at 3 centimeters per second, at 15 centimeters per second? This problem is kind of hard because we don't have a context to it. We don't have an actual problem that we're solving. They're just warming us up and getting us ready to plug stuff in. Okay? Things that we know, when we know we're finding dy dt, it says we know that we're looking at a specific time period where the time is 1 second or 1, right? My x at that time is 2, and the rate that x is changing with respect to time is 4. dx dt, the rate of x changing with respect to time is 4.
Why does it have at a time 1 again?
Okay, because the rate that x changes is not going to be 4 throughout all of time, right? It's saying at a time of 1, the rate that it's changing is 4. At a time of 2, the rate might be 6. At a time of 3, it might be 12, okay? So it's saying at the specific time of 1, which is where I'm looking at, the rate at which it changes is 4 at that specific moment. Okay, that's why it says that twice, okay? So we need to find the derivative. The derivative of what? Yeah, y equals x cubed, okay? So let's find the derivative of him. What's the derivative of y?
Oh.
Yeah, this is dy dt, and it's not dy dx anymore because we're doing it with respect to time, okay? What's the derivative of x cubed? 3x squared dx dt. Normally, we don't have to have a thing on the end of x, but we do because we're doing it with respect to time and not with respect to x. Make sense? Okay? That's our underlying variable that we're interested in, okay? Now,
If we're finding time, do we have to?
what?
If you're like, it's like when we're like doing the derivative of x, we don't need it because it's with respect to x. So if we're
Right.
doing it
So
time-
if time was in my equation, if this had like something time in there, like a t variable, then we wouldn't have to have it at all. It would be like dt dt, which goes away, right?
Okay.
Yes, good question. All right, now we just plop all our variables in. I don't even have a t variable, but they just say t is 1. Whatever, we're just looking at 1 second. I am finding dy dt, so this is what I'm trying to do, and I just plop everything else in. We know x is 2, so I'm gonna plug 2 in there, and dx dt is 4. So the rate that y is changing with respect to time is, I don't know, 48? 48, whatever, per whatever,
Is that our official?
right? Whatever per whatever. So maybe that's centimeters per second, or maybe that's
Isn't
feet
there
per
an
hour.
unknown variable or something like that?
What?
There's
Like
some-
units, they always just say units squared or whatever, like units per whatever second,
48.
yeah.
Like
So,
if they don't give us like a
I like
label, I thought
whatever.
there was something that with the U that we could just put in there. Units or something.
yeah, units usually. But we have 2 different units. We have like your distance units and then per whatever
So
our
you
time
could do
units
48 units per unit.
are. Sure, yep. And that's why this problem is hard because we don't have a story problem context to it. Like, I don't have any units. I don't know what to label it. This means nothing to me. But they're just warming you up. They're getting you used to the idea of doing that, okay? All right, so this one, example 2. Assume that oil spilled. Okay,
Shame. on
preview,
them.
look over top of this. I know, real quick, before we even read, I know I need an equation. I know I need something that I know, and I know I'm trying to find stuff, okay?
And you know there's
Equation, no, find. Do you see an equation in there?
Nope.
Nope. So sometimes we won't know the equation, but we have to go off of the geometric shape that they're talking about. So like up here they were talking about dripping stuff out of a cone. We know that we're using the equation for volume of a cone, right? Okay? And we have to find that. Like, what is that volume? Okay?
Are we
So
supposed
this
to have
guy-
those memorized?
No.
Okay.
In fact, in your calc book, in the front cover, back cover, front cover, one of them, it has, right here, it has all the shapes and what their formulas are on the front side. You see that? Okay, inside the front cover, it has the shapes and then whatever the formulas are, so you will have those. Assume that oil spilled from a ruptured tanker spreads in a circular pattern. Okay, now, here's the deal. It spills in a circular pattern. Okay, so we have this thing going on.
The equation of a circle.
The equation of a circle, and they're talking about area. You see the word area in there? So we need to know what we're talking about. Are we talking about area? Are we talking about surface area? Are we talking about volume? We're talking about area. And we're talking about of a circle. So area of a circle. That is the thing that we're focused on. Okay, do you know what area of a circle is?
Pi r squared.
Area equals pi r squared. Yes. That's my equation that I'm dealing with. Area equals pi r squared. Okay, things that we know. Whose radius increases at a rate of 2. Okay, what is increasing at the rate of 2? The radius is increasing. So radius increases at a rate, that's d r dt. So we know that d r dt equals 2. Do you see that? We know d r dt equals 2. Okay, how fast is the area increasing? What does that mean? What are we looking for? How fast the area increasing, that's d a dt.
2 in for that.
d a dt. When the radius is 60. When what equals 60?
The radius.
Just r, right? Do you see the difference between when we're talking about the rate of something is dr or d whatever dt versus the actual radius is that, right? Okay, now what do we do?
2 pi r d r.
Yeah, the derivative. We need to take the derivative, okay? So we do the left side and the right side. What's the derivative of a? d a dt, right? Okay? And pi r squared. Pi is not a variable. We don't have to do the product rule. Pi is a number, right? Okay, so the derivative of pi r squared is 2 pi r to the first power dr dt, right? And now we just plug junk in. We are trying to find d a dt. So I'm gonna like box around him and we have to plug everything else in. d a dt equals 2 times pi, the radius is 60, and then dr dt is 2. 2 times 2 is 4, 60 times 4 is 240 times pi, whatever that is. 754. Okay, now we have to figure out our units. dA, what's the units of area?
Square.
Yeah, something squared. What squared?
Feet.
Feet squared. So feet squared per, what's the units of time that we have in this case? Seconds. Do you see, did you pick up seconds somewhere?
That's a lot of feet
Seconds?
per second.
Yeah.
Better clean that up real fast.
754 feet squared per second. That's
I feel like
insane.
that was a good amount.
That's
of
a lot.
stuff learned.
Oh my gosh.
That's a lot.
I can finish my stats test real quick.
I feel like that's a good stopping point because we understand this.
You think so?
Yeah.
Okay, do 2 and 4 really quick on your homework.
Did I do my stats test?
Do 2 and 4. Okay, good place to start. If you're looking at a problem and you're like, where the heck do I even start? Start with these. Equation, no, find.
And then work for your derivative.
And then work for your derivative and then plop stuff in, okay? You're pulling stuff out of an equation like that, okay? Equation, no, find. Start with those. 2 and 4. Try to do those, okay?